At the heart of every galaxy lies one of the most mysterious objects in the universe, a supermassive black hole. Millions to billions of times the mass of our Sun, these giants power astrophysical jets, one of the most energetic processes known to physics. In 2019, the Event Horizon Telescope released this picture of the heart of M87, the first ever image of a black hole. A second image, released in March 2021, is helping astronomers understand the inner workings of astrophysical jets and the celestial giants that fuel them.
A quasar is a massive black hole that resides in the nucleus of most galaxies like our own and is smaller than our solar system, and yet through a variety of mechanisms it is able to outshine the whole galaxy around it. So it is a very mighty engine that's very small that is very, very powerful. If you look at the essential features of what we currently think is going on in the tiny nuclei of these galaxies, is that firstly, there is a black hole there which has this mass, but it has one other property which I believe to be very important, which is that it is spinning.
As a black hole spins, it draws charged particles, known as plasma, into its gravitational pull. These particles create a magnetic field that ejects energy thousands of light years into space.
Jets themselves comprise very hot gas and magnetic field, which together move with a speed that is very close to the speed of light. And following the precepts of special relativity, that means that any radiation that they emit will be beamed along their direction of motion.
In 1918, Heber Curtis discovered the first jet, which he described in his notes as a curious straight ray. As it turned out, that jet belonged to the supermassive black hole in M87.
So it's a rather special object in the life of an astronomer. I was a research student in Cambridge University in the early 1970s. This was in some sense a golden time for black holes. My friend and colleague Roman Znayak and I, we came up with a process which was able to extract energy from the spin of a black hole with an efficiency of roughly a half, and then we said, well, maybe this is the power source for the jets and much else besides.
The Blanford-Znayak process describes how a spinning black hole twists its magnetic fields into coils. This motion creates a current of electrons and positrons that flow out from the black hole in both directions, accelerated by the twisting magnetic fields. But until the recent Event Horizon Telescope image, this process was just a theory.
So what we see in our image is a spiral structure of the polarization, which tells us that the magnetic field is also spiral. To have a Blanford-Znayak process, first of all, you need ordered magnetic fields, which is what we see. Our image is ordered. And the spiral structure tells us that there's a component in the magnetic field around the disk, but there's also a vertical component, which means that there is a magnetic pressure that pushes out gas very close to the black hole. And this is also what the Blanford-Znayak process predicts. And this vertical component, we think, is a direct link to how the black hole is able to launch this jet. It is the most energetic process or powerful process in our universe.
These tiny nuclei, smaller than the solar system but containing massive black holes, can produce as much energy over their lifetimes as the stars that surround them. And so when we ask, well, how is the universe powered? Yes, there's gravity. Yes, there are stars. But these tiny but mighty galactic nuclei are big players too. And so they have a large role in the growth of what we see in the universe around us.
Stars begin their life as clouds of gas and dust in space, known as molecular clouds in stellar nurseries. All the stars you see in the sky, including the sun, started out in such gases. Gravitational forces cause these clouds to condense and contract, increasing the density and temperature of their cores. As the cloud continues to contract, it forms a dense, hot core called a protostar. This core continues to accrete more and more matter from the surrounding cloud. During this phase, the protostar is shrouded in a cocoon of gas and dust. When the temperature and pressure at the core of the protostar reaches a critical point, around 10 million degrees Celsius for most stars, nuclear fusion reactions begin. These reactions primarily involve the conversion of hydrogen into helium through a process similar to what occurs in the sun's core. The energy generated by these reactions provides the heat and light that make the stars shine, as well as the radiation pressure to hold off gravitational collapse. The balance between the inward force of gravity and the outward pressure generated by the fusion reactions keeps the star stable and in a state of equilibrium. Larger and more massive stars tend to be hotter and brighter, but also have shorter lifespans compared to smaller stars. For example, the lifespan of our sun, a medium-sized star, is about 10 billion years. It's about halfway through its life right now. But stars that are about 30 times more massive than the sun last only a few million years. Eventually, the core of the star runs out of hydrogen. When that happens, the star can no longer hold up against gravity. Its inner layers start to collapse, which squishes the core, increasing the pressure and temperature in the core of the star. While the core collapses, the outer layers of material in the star start to expand outward. The star expands to larger than it's ever been, a few hundred times bigger. At this point, the star is called a red giant. What happens next depends on the mass of the star. For stars like our sun, the radius at this stage may reach out to the orbit of Earth and swallow it, but its core will still have enough heat and pressure to cause helium to fuse into carbon, keeping the core from collapsing further. But once the helium runs out, the sun will shed most of its mass, forming a cloud of material called a planetary nebula. Its core, however, will cool and shrink, leaving behind a small, hot ball called a white dwarf. A white dwarf doesn't collapse against gravity because of the pressure of electrons repelling each other in its core. But for massive stars greater than about 8 times the mass of the sun, their fate is much more spectacular. These high-mass stars go through some of the same steps as medium-mass stars like the sun, with the exception that after helium runs out, their mass provides enough gravitational pressure to continue the fusion reaction. So after the supply of helium runs out, it is hot and dense enough to fuse carbon into neon. Fusion reactions occur until the core is filled with iron atoms. Up to this point, the fusion reaction put out energy, allowing the star to fight gravity. But fusing iron takes more energy than it produces, so the star eventually loses the battle against gravity. The core temperature rises to over 100 billion degrees as the iron atoms are crushed together until the repulsive force between positively charged nuclei overcomes the force of gravity, and the core recoils from the heart of the star in an explosive shock wave. This shock can propel the material away from the star at close to the speed of light in a tremendous explosion called a supernova. About 75% of the mass of the star is ejected into space in a supernova. So if the star prior to the explosion was 20 times the mass of the sun, after losing 75%, its core will be about 5 times the mass of the sun. For stars with leftover cores of anywhere from 1.4 to 5 times the mass of the sun, it will collapse into a neutron star. But if the core is larger, it will collapse into a black hole. So only stars with more than 20 times the mass of the sun will become black holes. The black hole forms when the remaining core of the supernova, because of its huge mass, is able to overcome quantum mechanical pressures which keep the core from collapsing in lower mass stars. The core continues to compress uncontrolled into theoretically an infinitesimally small volume. This means the entire mass of the core has compressed into zero volume. This is called a singularity. At least that's what our equations say. But infinities in our math equations usually indicate some kind of breakdown of the theory. So a singularity is probably an undefined realm of space-time which our current theories can't explain. According to scientists, a hypernova occurs when even larger stars, more than 30 times the mass of the sun, quickly collapse into a massive black hole. What distinguishes this explosion from other supernova explosions is that they are 10 to 100 times more powerful than a supernova. and that they result in a collimated beam of gamma rays, or put more simply, a narrow beam of gamma rays, similar to a laser that travels across the universe. These gamma ray bursts can last anywhere from fractions of a second to hours. They're highly energetic. A typical burst releases as much energy in a few seconds as the sun will release in its entire 10 billion year lifetime. They're rare. A few such bursts occur per galaxy every million years. But since there are at least 200 billion galaxies in the universe, and these rays have infinite reach, a few 100,000 of these occur every year somewhere in the universe. About 1 gamma ray burst is detected every day on Earth. But so far, every burst we've detected has occurred outside of our own galaxy. I should mention that besides supernovae, gamma rays can also be formed by very heavy mergers, such as when 2 neutron stars merge, or when a neutron star merges with a black hole. The biggest question you may have is, how does a narrow beam of gamma rays form? Shouldn't these photons be emitted spherically, just like the way the matter is expelled from the hypernova? The interesting thing is that when scientists first discovered these gamma ray bursts, calculations showed that the source of the explosion would have more energy than the Big Bang itself, which was not possible. But this calculation was based on a spherical photon burst. When they discovered that the burst actually occurs in a narrow beam, the energy numbers became much more realistic. The exact mechanism of the formation of this beam is not settled science, so I'll tell you what scientists speculate is going on. What we do know is that it comes out in 2 jets in opposite directions. It has to be in 2 opposite directions so the momentum of each cancels out. The hypothetical mechanism is the following. The material ejected from the explosion is a plasma, which results from gases heated to such extremes that they lose electrons from their atoms. In addition, the rapid rotation of the dying star twists up its magnetic field. This means that the easiest path of escape for any of the charged particles being ejected from the hypernova is along a narrow beam at the poles of the rotation, since the magnetic field can't get as tangled in that direction. The particles being ejected are largely electrons. The twisted magnetic field causes the electrons to travel in a kind of helix, like a DNA molecule. If the electrons are moving fast enough, the rapid change of direction can produce high-energy photons, or gamma rays. Gamma rays can also form if extremely fast electrons crash into photons. The transfer of energy to the photon can cause it to gain energy and become a gamma ray. The other question you might have is, can one of these things kill us? First, let me point out that, as I said earlier, they are quite rare within our galaxy. They might occur a couple of times every million years or so. If the beam is not directly pointed at us, then we should be fine. Since the gamma ray beam is collimated like a laser, it does not spread out much, like the light from a lamp. So there's a low probability that it would just happen to be directly pointed at us. Also, if the burst originated far enough away, then we might be protected because space is not completely empty, and the beam could collide with other celestial bodies between us and the origin of the beam, diffusing the ray and making it harmless. But if it's pointed directly at us, within our galaxy at about 200 light years or closer, it would cause a global extinction event. It would burn our atmosphere and vaporize our oceans. But even at greater distances, from within our own galaxy on the order of 1,000 or more light years away, it would still sterilize life on the side of Earth pointed towards the burst. Such a burst is believed to have caused a mass extinction on Earth about 443 million years ago. A hypernova is the most energetic event in the universe, exceeded only by the Big Bang. Could it happen again? Sure, it's a possibility. There are about 100,000 stars within a 200 light year radius of Earth. Although scientists haven't discovered any stars in this vicinity that are large enough to explode in a hypernova, you might take some comfort knowing that if we do get hit, we will not see it coming. Since gamma rays are a form of light, they travel at the speed of light, so we would have no warning. In addition, they are completely invisible anyway, because their frequencies are too high for our eyes to detect, even higher than X-rays. We in the Earth would just fry with no warning whatsoever.
Imagine that you have a taxi cab that is streaking down Fifth Avenue in Manhattan at a speed very near the speed of light. And you're watching this very fast-moving taxicab. What would that look like? Well, let me just show you a little animation of it. Now, of course, we're imagining that the speed is close to the speed of light. That's a little hard in everyday life, but we can do it in animation. And look at that taxicab. Isn't that strange, right? The taxicab is shrunken in the direction of motion. Only the height of the taxicab is unchanged. It's that its length has been squeezed down by this factor of gamma. Now, you note something else. If you look at that picture a little bit more carefully, it's not only that the taxicab is squeezed along the direction of motion, it's also twisted a bit, right? We're seeing the back bumper at a kind of funny angle relative to what you might expect. And the reason for that is that we are in a situation with relativity where there's a difference between what's actually happening out there in the world and what we perceive when we consider the rays of light bouncing off of an object. And if you consider the rays of light bouncing off of the taxicab, you're actually seeing the taxicab at different moments in time, different points on it, because the light from different locations on the taxicab have to travel different distances to your eyeball, and therefore you're not seeing the taxicab, the whole thing at one instant of time. You're seeing different points on the taxicab at different moments in time, dependent on how far away those points on the taxicab are from your eyeball. And when you take that complexity into account, you get that interesting twisting effect that you're seeing in the animation. But the bottom line of what's actually happening to the taxicab from our perspective is what we derive mathematically. Its length in the direction of motion is being shrunken by a factor of gamma. Now imagine that you were inside of that taxicab. How would things look from your perspective? Well, from your perspective, the taxicab is not moving relative to you. In fact, as we've emphasized, if you're moving at a fixed speed in a fixed direction, you can claim to be at rest, and it's everything else that's rushing by you in the opposite direction. So from your perspective, it's life as normal inside of the taxicab, and if you look out the window, it'll be the outside world that has all this weird stuff happening with lengths being contracted, and again, based upon the light travel time, interesting twisting and curving from your perspective. So let me show you that alternative perspective. Here it is. So there you are inside the taxicab. Everything appears normal inside, but look at what things look like on the outside. Things are shrunken, they're kind of twisted because of the weirdness of the rate at which different clocks are ticking and the different distances that the light has to travel, all folded into this length contraction in the direction of motion.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.